In the first unit of this topic, you learned that energy conversion, work, power, and efficiency are not things that just randomly happen in a power plant. They're governed by scientific principles at work in the universe and are controlled in the plant by you, the operator. By understanding the theory behind these principles, you're better prepared to understand, explain, and predict the outcome of any action that you take. In this unit, we'll look at a few of the scientific properties of matter. The properties we'll cover include weight, mass, density, specific gravity, specific volume, and viscosity. To perform your job properly, you must understand how matter behaves and what its properties are. For example, viscosity is the basis by which lubricants are identified and classified. Specific gravity is the basis for testing storage batteries to determine if they are properly charged. And specific volume is a key property for understanding how and why the steam cycle works. In this unit, you'll learn the theory behind viscosity, specific gravity, and specific volume. And you'll see how they apply to the day-to-day operation of a power plant. Finally, you'll learn about pressure exerted by a fluid and fluid flow. To understand properties of matter, we must learn what mass and weight are. And we must understand the relationship between the two. Mass has two characteristics. First, the mass of an object is the amount of matter contained within the object. Second, the mass of an object determines how fast an object will accelerate when a specific force is applied to it. Mass is difficult to measure directly. Weight, though, is simple to measure. It's the result of the gravitational forces acting on mass and can be measured on a scale. Now, weighing an object is a convenient way of measuring mass, but as you'll see, it does have its limitations. Now, these astronauts exhibit the properties of mass and weight. While on the surface of the Earth, each astronaut has a definite mass and a definite weight, which can be easily measured. When the astronauts go from the Earth to the surface of the Moon, mass, because it's a physical property, remains constant. However, weight becomes less because the gravitational force of the Moon is less than the gravitational force of the Earth. This has to do with the fact that weight must be opposed in order to be measured. For example, on the Moon itself opposes the force of gravity. However, when an astronaut moves out into space, there's nothing to oppose gravity, and his weight is zero. His weightlessness allows him to float freely in space. His mass, on the other hand, continues to remain unchanged. Variations in weight result from changes in the gravitational forces acting on an object. Since the gravitational force at the surface of the Earth is constant, the weight of an object doesn't change as long as it remains on the surface of the Earth. That makes it easy to convert between mass and weight. 1 pound of mass and 1 pound of weight on the surface of the Earth have the same meaning for all practical purposes. To simplify things throughout the rest of this unit, we'll use weight in our calculations. Another thing we want to consider is what causes objects or fluids to move. That is, unbalanced forces. Take, for example, this coal car. While the coal is in the car, the bottom of the car pushes up with a force equal to the coal pushing down. The forces are balanced. As long as the bottom is strong enough to support the coal, it will remain in the car. When the coal car is turned, there isn't anything to counteract the downward force of gravity acting on the coal, and the coal falls out of the car. We can say, as a general rule, that an object which moves does so because imbalanced forces act on it. Okay, you now know that there is a difference between mass and weight. But for our purposes, the difference isn't critical, and we'll use weight throughout this unit. You also know that objects move when forces are unbalanced and remain stationary when forces are balanced. And you've seen an application of the physical property of weight in the coal yard. We'll stop here so that you can read the material in the text and answer the questions. When we come back, we'll look at density and specific gravity. Weight, as you know, is the measurement of the gravitational force of the Earth acting on mass. Weight is used to determine the two things we'll talk about in this segment: density and specific gravity. Density is a comparison between the weight of a material and its volume, while specific gravity is a comparison between the density of water and the density of some other material. When we talk about the density of a material, we're talking about its weight per unit volume. Density is symbolized by the Greek letter rho. The equation used to determine density is rho is equal to weight divided by volume. Density can be measured using a number of units, the most common of which are pounds per cubic foot and pounds per gallon. There are conversion factors that can be used to convert between the different units. You should know these conversion factors because we'll be using them later on. 1 gallon is equal to 0.134 cubic feet, and 1 cubic foot is equal to 7.5 gallons. Well, now let's determine the density of this solid object, labeled Block A. The first step is to weigh the object, and we can do this using this scale. It's marked off in tenths of a pound. Now, according to our scale, the weight of the object is 0.7 pounds. Well, now we have to calculate volume. As you know, the volume of an object is equal to its length times its width times its height. Now we can measure the dimensions using a ruler. It's 8 inches long, three and a half inches wide, and 1.5 inches high. Now we multiply these together and we find that the volume of the object is 42 cubic inches. To convert cubic inches to cubic feet, we use the conversion factor. 1 cubic inch is equal to 5.787 times 10 to the minus 4 cubic feet per cubic inch. Multiplying 42 cubic inches by our conversion factor gives us a volume of approximately 0.024 cubic feet. We've now determined the weight of the object and its volume. We can put these figures into our equation for density. Remember, we said density is equal to weight per unit volume. 0.7 pounds divided by 0.024 cubic feet equals about 29 pounds per cubic foot. The density of this object is about 29 pounds per cubic foot. And what this means is that if we have 1 cubic foot of this material, it will weigh about 29 pounds. Well, let's see how the density of this object compares to Block B, made from a different material. As you can see, both objects are the same size. But this one weighs less, only 0.1 pound. And like the first object, it measures 8 inches by 3.5 inches by 1.5 inches. So, its volume is also 0.024 cubic feet. Now, putting these figures into our equation, we find that 0.1 pound divided by 0.024 cubic feet gives us a density of about 4 pounds per cubic foot. Let's look at this chart, which illustrates the relationship of volume, weight, and density. Two objects with identical volumes, but different weights, will have different densities. We can also conclude for objects of the same volume, the more one object weighs, the denser it is. Now, so far we've been looking at the density of a solid object. Well, what about the density of a liquid, such as water? We can find the density of a liquid the same way we found the density of a solid, by measuring its volume and weighing it. First, we'll put an empty container on the scale. And we'll set the reading to 0. Now this cancels the weight of the container and allows us to read the weight of the water only. Next, we put an identical container of water on the scale. Its weight is about 1.04 pounds. Now this container is designed to hold 1/8 of a gallon. We now have the information we need to figure density. The density of this container of water is equal to weight, 1.04 pounds, divided by its volume, 1/8 of a gallon. 1/8 of a gallon can be written as 0.125 gallons. When we divide the numerator by the denominator, we get a density of 8.32 pounds per gallon. If we need to convert this to cubic feet, we do it this way. 8.32 pounds per gallon times the conversion factor, 7.5 gallons per cubic foot, gives us 62.4 pounds per cubic foot as the density of the water. Remember this value, 62.4 pounds per cubic foot as the density of water. We're going to use it again in a few minutes. What we've just seen is that density is the weight per unit volume. And keep this in mind as we look at another property of materials, specific gravity. Specific gravity is the measure of the density of a material in relation to the density of water. Specific gravity is equal to the density of a material divided by the density of water. From the last experiment that we did, you know that the density of water is 62.4 pounds per cubic foot. To find the specific gravity of water, we divided the density of the material, in this case water, by itself. That's 62.4 pounds per cubic foot divided by 62.4 pounds per cubic foot. The units cancel, and we're left with 62.4 divided by 62.4, which is equal to 1. Now this makes sense if you consider that we're comparing water to itself. So, the specific gravity of water is 1. Now, notice that there are no units for specific gravity. 1 is used as a reference. Specific gravity tells us if a material is more or less dense than water. A material with a specific gravity greater than 1 is more dense than water and will sink in water. A material with a specific gravity less than 1 is not as dense as water and will float in water. Let's go into a lab where we can illustrate this point with these two different lubricants used in a plant. In most cases, lubricants are less dense than water and will float, but this isn't always the case. Watch what happens when we pour each lubricant into a container of water. The first lubricant sinks to the bottom, while the second lubricant floats on the surface of the water. Without doing any calculations, we immediately know that the first lubricant has a specific gravity greater than 1, and the second lubricant has a specific gravity less than 1. In a plant, the specific gravity of liquids can be measured using a hydrometer. You'll use a hydrometer when testing the charge on a storage battery. In the next segment, we'll show you how the principle of specific gravity is used to test storage batteries. Then we'll go on to look at specific volume and viscosity. For now, though, read over the material in your text and answer the questions. If you have any questions about the material, ask your instructor to help you. In the last segment, you learned that specific gravity is the measurement of the density of a material in relation to the density of water. You also learned that the specific gravity of water is equal to 1. In this segment, we'll apply what you've learned about specific gravity to an important job, testing the charge on plant storage batteries. Later on in this segment, we'll cover two other properties of materials, specific volume and viscosity. A typical storage battery, which supplies emergency DC power to a plant, is composed of a number of individual cells that are connected together in series. Each cell is made up of a positive and a negative plate, insulated from each other by separators. The cells are immersed in a solution called electrolyte, a mixture of sulfuric acid and water. An acid-resistant jar encases the entire assembly. The specific gravity of the electrolyte is a function of the amount of acid in the water and is a good indication of the charge on the battery. The specific gravity of the electrolyte is affected by temperature, so as we'll see, specific gravity readings must be corrected for temperature. Most storage batteries, when fully charged, have electrolyte at a specific gravity between 1.2 and 1.3. On the job, specific gravity is measured using a hydrometer. A hydrometer is basically a syringe, a glass barrel with a rubber bulb on one end. Inside the glass barrel is a float. A hydrometer is usually accurate to 3 decimal places, so a typical reading might be 1.286. Since this many decimal points can be awkward to work with, it's customary to multiply the specific gravity by 1,000, so that 1.286 becomes 1,286. Checking specific gravity with a hydrometer is a normal part of periodic battery testing. Each cell must be tested individually, and the reading is recorded so that it can be compared with previous results. To make a specific gravity check, squeeze the bulb, then place the hydrometer's nozzle in the cell. Release the bulb so that electrolyte is drawn into the barrel. The float rises. Wait till the float stops moving. Then read the scale on the float right at the surface of the liquid. Each division on the float is equal to 5 thousandths. This cell reads about 1,220. After taking the measurement and recording it, squeeze the bulb again and return the electrolyte to the cell. Then move on to the next cell and repeat the procedure. In order to get accurate specific gravity readings, 2 considerations are necessary. First, the hydrometer tests should not be made right after water has been added to the battery. After adding water, it's best to charge the battery for a specific period of time to give the water time to thoroughly mix with the electrolyte. Otherwise, the water will sit on top of the denser sulfuric acid solution, giving you a false reading. The second consideration is temperature. Most hydrometers are calibrated to give correct readings at 77 degrees Fahrenheit, 25 Celsius. Higher or lower temperatures will make the electrolyte more or less dense. Therefore, hydrometer readings must be corrected for differences in temperature. A pilot cell is typically used to make temperature corrections. A pilot cell is nothing more than a specific cell chosen to be representative of all cells in the battery. The pilot cell has a thermometer that is usually calibrated to directly indicate correction factors for different temperature readings. The thermometer on this pilot cell shows a temperature of 73 degrees Fahrenheit, approximately 4 degrees colder than the base temperature of 77 degrees. The scale on the right-hand side of the thermometer indicates the specific gravity correction factors for temperatures above or below 77 degrees. This temperature is halfway between 0 and -2 on the scale. The correction factor is -1. A reading of 1,220 with a -1 correction factor gives us a corrected reading of 1,219. All of the readings for individual cells are corrected in this manner. For a typical lead-acid battery, if the corrected readings are all above 1,200, this indicates there is a good charge on the battery. All right, now that you know what specific gravity is and how it can be used to test the charge on storage batteries in the plant, let's move on to specific volume. A specific volume is the measure of the space occupied by 1 pound of material. Basically, this means that specific volume is the inverse of density. Mathematically, specific volume is 1 divided by density. You'll recall that the units of measure for density are pounds per cubic foot or pounds per gallon. The units of measure for specific volume are typically cubic feet per pound, or occasionally gallons per pound. To calculate the specific volume of material, you can use the equation specific volume is equal to volume divided by weight, or you can simply figure it out as 1 over the density. Now, in the last segment, we calculated the volume of this block and found that it has a volume of 0.024 cubic feet. If we divide its volume by its weight, which is 0.7 pounds, we get its specific volume in cubic feet per pound. Doing the math, we find that the specific volume of this material is 0.034 cubic feet per pound. Now, we can also calculate specific volume by taking the inverse of density. Let's do this for water. You know that the density of water is 62.4 pounds per cubic foot. Dividing this through, you get the specific volume of water equal to 0.016 cubic feet per pound. Specific gravity and density are very similar, but each has its own particular application. In later units, you'll need to understand specific volume in order to calculate the properties of steam and water as they relate to the plant cycle. For now, though, let's go on to look at viscosity. Viscosity, which is the measure of a fluid's internal resistance to flow, is most often associated with lubricants. In the lab, we can easily demonstrate the property of viscosity by comparing two different lubricants as they're poured. The lubricant on the right has a low viscosity. It is thin and flows quickly from the beaker. However, the lubricant on the left is thicker and flows much slower. It has a higher viscosity. Therefore, we can say it has a greater internal resistance to flow than the lubricant on the right. This is evident by the additional length of time it takes for the lubricant to flow from the beaker. Another factor that has a great effect on viscosity is temperature. To illustrate this point, we'll perform another experiment using two samples of the same lubricant. One sample has been carefully heated, while the other sample remained at room temperature. As you can see, when the lubricants are poured, the sample on the left, which has been heated, flows more rapidly from the beaker. Its viscosity has been lowered by increasing its temperature. However, the same lubricant at room temperature has a higher viscosity. It is thicker and flows from the beaker at a slower rate. As a rule, higher temperatures cause viscosity to decrease, while lower temperatures increase viscosity. A special instrument called a Seybolt viscometer can be used to measure viscosity. Even though you might never use one, we'll show you how it works so you'll have a better idea of what viscosity means. A typical Seybolt viscometer has an upper section with several chambers housed in an oil bath. The oil bath maintains the fluid in the chambers at a constant temperature. The lower section contains a flask for collecting the oil drained from an upper chamber. To use the viscometer, an oil sample is first poured into one of the upper chambers. Then there's a waiting period for the sample to reach the same temperature as the oil bath. Next, a plug is removed from the upper chamber with the oil, allowing it to flow into the flask. A stopwatch is started the moment the oil is released from the chamber. The number of seconds it takes for the fluid to fill the flask to the mark on the neck is the viscosity of the fluid, measured in Seybolt seconds universal, or SSUs for short. As you can see, the viscosity of this lubricant is 35.77 SSUs. Now, viscosity is an extremely important consideration when choosing lubricants. For a lubricant to work, it must be thin enough to flow between moving parts, but not so thin that it will be squeezed out from between them. If a lubricant with too low or too high a viscosity is used, a film of lubricant will not form between the moving parts, and the bearings and lubricated parts of the equipment will be damaged. Most plants have a system for helping you identify which lubricant goes with which piece of equipment. You'll have to find out how the system in your plant works. One typical system uses color. Each piece of equipment is color-coded so that the equipment has the same color as the pump on the lubricant drum. To select a lubricant, you find the pump that matches the color code on the equipment. You can then draw the lubricant that you need. Okay, now you've seen how specific gravity can be measured and used to test storage batteries in the plant. You've learned how to calculate the specific volume of a substance and how viscosity is measured. In the next segment, we'll consider pressure. For now, read the material in your text and answer the questions. Remember, if you have trouble following any of this material, ask your instructor to help you. Within the complex world of a power plant, miles of piping in every conceivable size and shape are used to carry fluids from one place to another. Hundreds of gauges and thousands of feet of tubing are used to indicate the condition that the plant is in at any time during the day or night. Valves of every size and type are used to maintain systems within specified limits or to safeguard systems against possible damage. Well, what do these things and a majority of the components in the power plant have in common? They all depend on pressure in some way to do their job. In this segment, we're going to look at pressure and see how it relates to fluids in the plant. Pressure is defined as force per unit area. The equation for calculating pressure is pressure is equal to force divided by area. Now, the force in question is in many cases weight. So we can also write the pressure equation as pressure is equal to weight divided by area. As you know, weight can be measured in pounds, and Area is commonly measured in square inches, so the units we'll use for pressure are pounds per square inch, which is written PSI. Now next we'll look at pressure in a column of fluid. One thing to keep in mind is that in a column of fluid, the pressure exerted at any point in the column is dependent on the weight of fluid above that point. We can get an idea of the amount of pressure exerted by a column of water if we look at this container. It measures 12 inches in height, 12 inches in width, and 12 inches in depth. The container holds a cubic foot of water that is exerting a pressure on the sides and bottom of the container. Let's figure out how much pressure is exerted on the bottom. We'll need to know the weight of the water and the area it's acting on. Remember, the equation for pressure is weight divided by area. The bottom of the container measures 12 inches by 12 inches, so its area is 144 square inches. From our earlier discussion, you know that a cubic foot of water weighs 62.4 pounds. Putting these figures into our pressure equation will tell us the pressure exerted on the bottom of the container. Pressure is equal to 62.4 pounds divided by 144 square inches. The pressure exerted on the bottom of the container is 0.433 pounds per square inch. From this, we can conclude that a 1-foot column of water exerts a pressure of 0.433 pounds per square inch. Well, let's compare this with a container that's 24 inches wide, but still 12 inches high and 12 inches deep. Now, this container holds 2 cubic feet, and its bottom has an area of 288 square inches. The weight of 2 cubic feet of water is equal to 2 times 62.4 pounds, or 124.8 pounds. So the weight of the water has doubled, and the area of the bottom of the container has also doubled. Putting these figures into our equation, we get pressure equal to 124.8 pounds divided by 288 square inches. Doing the math, we see that the pressure exerted on the bottom of the container is still 0.433 pounds per square inch. Now, there must be a reason for 2 different sized containers having the same amount of pressure exerted on the bottom. Well, what do the containers have in common? The height of the column of water in both is the same, 12 inches. We've seen what happens when the area changes from 1 square foot to 2 square feet, but the height of the water remains the same. The pressure also remains the same. So we can conclude that regardless of the area, the pressure exerted by a column of water is determined by its height above the point being measured. Well, let's see if this conclusion holds true. We'll turn the second container up on its end so that it now looks like this. The area of the bottom is now 144 square inches, and there is a 24-inch column of water exerting a pressure on the bottom. The weight of the water hasn't changed. It's still 124.8 pounds, but the area is now 144 square inches. If our conclusions are correct, the pressure exerted on the bottom should be double what we had in the last example. Well, let's see. Pressure is equal to 124.8 pounds divided by 144 square inches. Now, this works out to be 0.866 pounds per square inch, just double of what we got in the last example. We can conclude that doubling the height of water in a column will double the pressure exerted on the bottom of the column. All right. What have we learned about pressure so far? Well, pressure is the force acting on a unit area. We also know that pressure exerted by the water in the container is not determined by the size or volume of the container, but rather by the height of water in the container. Let's look at one more example and compare the pressure exerted by water to the pressure exerted by another fluid. Now, this container, which we used earlier, is filled with 1 cubic foot of mercury that weighs 848.64 pounds. The area of the bottom of the container is 144 square inches. Let's put these figures into our equation and calculate the pressure exerted by the mercury on the bottom of the container. Pressure is equal to weight divided by area. So, our equation reads, pressure is equal to 848.64 pounds divided by 144 square inches. This equals 5.89 pounds per square inch. Now, the container in this example is the same size as one that we used earlier to calculate the pressure exerted by water. But the pressure exerted by mercury is greater than the pressure exerted by water. Why? Because mercury is denser than water. Density affects the pressure exerted by a fluid. Now, regardless of the size of the container, pressure will be determined by the height of fluid above the surface where the measurements are being taken and the density of the fluid being measured. This can be expressed mathematically. Pressure of any column of liquid is equal to the height of the column times the density of the material. Now, remember this equation because we'll see it again in the next segment. For now, take some time to review this material in the text and answer the questions. If you have any trouble understanding this material on pressure, ask your instructor to help you. When we return, we'll begin talking about pressure and the flow of fluids. You know that the pressure exerted by the fluid in this tank is determined by the density of the fluid and the height of the fluid above the point where the pressure measurement is taken. Now, if all we do is store fluid in a tank, we don't have to be too concerned about pressure or fluid flow. But you probably already know that not only do we store fluid, but we also have to move the fluid around. To know how this is done, we have to understand the principles behind fluid flow and how they're related to pressure. And that's what we'll look at in this segment. Flow is caused by a pressure differential. As long as pressure across a fluid is equal, no flow occurs. However, when there's a difference in pressure, fluids flow. Now, flow is always from an area of higher pressure to an area of lower pressure. A pressure differential can be exerted on fluids in a number of ways, one of the most common being a pump. Another way of creating a difference in pressure between two fluids is to raise the level of one fluid above the other. Let's see how this works using these two 30-foot tanks. Tank A is filled with 30 feet of water, and Tank B is filled with 5 feet of water. The tanks are connected to each other by a line that has a valve installed in it. Right now, the valve is closed. We'll put a pressure gauge on each side of the valve so that we can monitor the pressure in each tank. Pressure in Tank A is 13 psi, while the pressure in Tank B is about 2 psi. That is about an 11 psi difference in pressure between the two tanks. This means that there should be flow between the two tanks because there is a pressure differential. But because the valve in the line is closed, there is no flow. Let's watch what happens when we open the valve. As the valve is opened, water flows from Tank A, where the pressure is higher, to Tank B, where the pressure is lower. When the levels, and therefore the pressure in the tanks, become equal, there is no longer a differential pressure, and flow stops. Notice that the gauges on each side of the valve are reading the same. The pressure is now equal in both tanks. Tanks are commonly used to create a suction head for pumps. Head is simply a term used to describe the height of a fluid. If a tank is connected to the suction of a pump, the height of fluid above the suction is the suction head, and it determines the amount of pressure at the suction of the pump. Most pumps require a certain amount of suction head in order to operate properly. The amount of head required is usually expressed in feet. For pumps which move water, head in feet can be converted to pounds per square inch by multiplying the head of the fluid times 0.433 pounds per square inch per foot. To calculate the suction pressure on a pump with a 20-foot head of water at its suction, we'd multiply the head, the 20 feet, times 0.433 pounds per square inch per foot. Feet cancel, and the equation equals 8.66 pounds per square inch of pressure. In other words, a 20-foot head of water exerts a pressure of 8.66 psi. If the pump moves some fluid other than water, head can be converted to pounds per square inch by multiplying the density of fluid times the head, expressed in feet, divided by 144 square inches per square foot. Now, head and suction, as we've used them so far, have been applied to a static system. That is, a system where no flow is occurring. When there is flow in a system, head can be broken down into 4 types: static head, velocity head, friction head, and total head. Now, we'll explain what each of these terms means by using this simple gravity-fed system. But keep in mind that the principles discussed here also apply to a pump-fed system. Now, we'll explain static head first. The vertical distance, usually expressed in feet, from the top of a column of fluid to its discharge is called the static head. Velocity head, which we'll discuss next, is the pressure that results from fluid flow. We'll start a flow into and out of this tank. We'll make the discharge equal to the input so that the level in the tank remains constant. The distance that a fluid rises when discharged vertically from the tank is called the velocity head. Velocity head is less than the static head. The difference between the static head and the velocity head is caused by friction. The drop in pressure caused by friction is the friction head. We can illustrate friction head if we make a few modifications in our drawing. We've added some standpipes to the discharge line. At the end of this row of standpipes, we've installed a valve. With the valve closed and no fluid flow through the system, the level of the fluid in the tank and in the standpipes is equal. We'll open the valve and at the same time start a flow of fluid into the tank to keep the tank level constant. As we do this, notice that while the level in the tank remains constant, the level of fluid in each standpipe decreases. The decrease in level means that the further the fluid must flow in the discharge pipe, the greater the friction head. Friction head, velocity head, and static head determine total head on a system. Total head is defined as static head plus velocity head minus friction head. All right, we've looked at the different categories for head that are used in a plant. For right now, all you need to be concerned with are their definitions and functions. In a later unit, we'll apply this material to flow within a system. Up to this point, we've only considered the pressure exerted in an open tank by a column of fluid. This pressure is exerted in the downward direction and is greater at the bottom of the column than the top. An additional pressure can be exerted if the tank is sealed and pressurized with a pump. In this case, the additional pressure will be applied equally over every square inch of the tank. This means that the pressure in the tank will be the pressure from the pump plus the pressure exerted by the column of fluid inside the tank. Applying pressure with a pump to a sealed system is called hydrostatic testing and is often done to test systems after maintenance has been done on them. You'll find hydrostatic testing being done to boilers in order to test repairs that have been made on the boiler tubes. Hydrostatic tests are an important step in ensuring that equipment has been installed properly or repairs have been done correctly so that the system does not leak. During hydrostatic testing, it is very important that the pressure being applied to the system does not exceed the manufacturer's specifications for the maximum allowable pressure on the system. Exceeding this pressure could cause the system to rupture. In this segment, you've looked at the principles behind fluid flow. You found out that fluids flow when there is a differential pressure, and that flow is from an area of higher pressure to an area of lower pressure. You've seen the different types of head in a system where flow is occurring. And finally, you've learned what hydrostatic testing is. Well, take some time to review this material in your text and answer the questions. In the next segment, we'll discuss flow rate. Flow is a critical part of power plant operation. There's cooling water flow, fuel flow, steam flow, and hundreds of other flows that an operator must keep track of. As you can see, an operator really can't get by without having some understanding of what flow is. Flow is defined as the amount of fluid that moves past a point in a specified unit of time. Now, we can consider this amount in two ways, either as volume or as mass. When we consider the amount as volume, we're considering the volume of fluid that passes a given point in a given period of time. This is called volumetric flow rate. There are many different units for measuring volumetric flow. Typically, cubic feet per minute or gallons per minute are used. But units such as gallons per second or cubic feet per hour can also be used. When we consider the amount of fluid as mass, we're measuring the mass of fluid that passes a given point in a given period of time. Now, this is known as mass flow rate, which is typically measured in pounds per hour or tons per hour. But like volumetric flow, other units are sometimes used. Tons per day is one example. One place where the measurement of flow is important is when fluid is transferred from one tank to another. If you need to fill this 80,000-gallon storage tank with water, you'll want to know how long it will take. To find this out, you need to know the flow rate at which the water is pumped. Let's say this pump, which fills the tank, is operating at its rated capacity of 80 gallons per minute. How long will it take to fill the tank? In this case, if we divided the capacity of the tank, 80,000 gallons, by the flow rate, 80 gallons per minute, the gallons cancel, and we find that it will take 1,000 minutes to fill the tank. If we want to know how many hours there are in 1,000 minutes, we divide 1,000 minutes by 60, because there are 60 minutes in an hour. We find that it will take a little more than 16 1/2 hours to fill the tank. Knowing how long it will take helps you to know how often the tank must be checked while being filled. It also lets you know when you must begin watching the tank carefully to prevent it from overflowing. Understanding flow and flow rate helps you determine how much fluid has been pumped. Well, let's say that you've been transferring oil to this tank for 2.5 hours at a rate of 9 gallons per minute. How much fluid has been transferred? To find the amount of oil that has been pumped, we multiply flow rate by the hours we've been pumping. That's 9 gallons per minute times 2.5 hours. To convert hours to minutes, we also need to multiply everything by the conversion factor, 60 minutes per hour. The hours cancel, the minutes cancel, and multiplying everything out, we find that 1,350 gallons have been pumped into the tank. Now, flow is affected by many factors. To really understand flow rate, you need to know some of the factors that affect flow. The factors we'll discuss are head, viscosity, wall roughness, pipe length, and pipe size. Now, for this discussion, we're going to limit ourselves to talking about fluids such as water, which are incompressible. Other fluids, such as gases and steam, are compressible and act differently. So keep in mind that what we talk about applies to incompressible fluids only. So far, we've only discussed flow caused by a column of water. But in the plant, flow is most often generated by pumps. And pumps require a certain amount of pressure at the suction. Now, this pressure, called the suction head, can be provided by a tank. When suction head increases, flow also increases. This tells us that head has a positive effect on the flow rate of fluids. But at all times, a minimum amount of suction head must be available at the pump suction. If suction head decreases below the minimum value, problems occur, and the pump may be damaged. Viscosity is the second factor that affects flow rate. Remember, we defined viscosity as a fluid's internal resistance to flow. When viscosity increases, flow decreases. So we can say that viscosity has a negative effect on flow. Now, the negative effect of viscosity is apparent if we consider two identical pumps. One that pumps thick oil and the other that pumps water, which is much thinner by comparison. If all other factors are equal, the flow rate for water will be much higher because the water has less internal resistance to flow. To overcome this problem, when pumping some types of oil, it's sometimes necessary to heat the oil in order to lower its viscosity. The third factor that affects flow is wall roughness in a pipe. The rougher the wall of a pipe, the greater its resistance to the flow of fluids. By contrast, the smoother a pipe wall is, the less resistance it offers to flow. Corrosion of the inside of a pipe can increase wall roughness, resulting in a decrease in flow. The fourth factor we'll discuss, pipe length, is affected by friction in the pipe. The longer the pipe, the greater the friction, and consequently, the greater the resistance to flow. The final factor we'll look at is pipe size. In general, increasing the size of the pipe through which fluid flows will increase the flow rate. However, flow through a pipe is very complicated because of the many things which affect flow. We'll simplify our discussion by only considering those aspects of the flow that you'll be able to see in your job. In a long run of pipe such as this, the velocity of the fluid, which in this case is water, remains the same throughout the pipe. The reason for this is simply that since the fluid is incompressible, what's going in one end at a given rate has to be coming out the other at the same rate. While velocity remains the same over the entire length of pipe, pressure, symbolized by the letter P, drops. This is always true because flow couldn't occur without differential pressure. Now, let's compare velocity and pressure in two different sized pipes. We'll connect the pipes to two identical pumps and establish the same total flow through each pipe. The amount of flow and pressure at the inlet of each pipe is the same, but flow velocity, symbolized by the letter V, is less in the larger pipe than the smaller pipe. Now, this makes sense if you consider that since there is less space inside the smaller pipe, the water must move faster in order to have the same flow rate as the larger pipe. Well, now we know that pressure at the outlet of each pipe will be lower than the inlet pressure. And the question is, will the outlet pressure in both pipes be the same? It turns out that the outlet pressure will be lower in the smaller pipe than in the larger pipe. The reason for this is that the conversion of fluid velocity to pressure is not the same in two different sized pipes. In the smaller pipe, there's more fluid velocity and less pressure. In the larger pipe, there's less velocity and more pressure. We can conclude from this that if we go from one pipe size to a smaller pipe size in a system, velocity and pressure will change. In this segment, you've seen several examples of why an understanding of flow rate is important to you as an operator. You've also learned some of the factors that affect flow and the characteristics of flow through a pipe. Throughout this unit on properties of material and fluid flow, we've shown you certain properties of material and how they affect the day-to-day operation of a plant. And we've related some of these properties to one aspect of plant operation, fluid flow. You've learned what it is and how it's affected. Take some time to review the material in your text and answer the questions. If you have any trouble understanding any of the information in this unit, ask your instructor to help you.